Terry Wallace is the Director Emeritus of Los Alamos National Labs. He was the 11th director of the lab and also served as Director of Global Security and Science Intelligence Officer. He has a bachelor's degree in mathematics and geophysics from New Mexico Tech, and he has a PhD in geophysics with a concentration in seismology from California Institute of Technology. About 20 years, he was a professor of geosciences and applied mathematics at the University of Arizona. In 2003, he was awarded the Carnegie Mineralogical Medal by the Carnegie Institution. And he has many books and articles on mineralogy for mineralogists. So here we are with Terry's presentation on silver, the magical mineral maker.
So I'd like to talk today about silver. Yesterday we did gold, but silver. Silver is even more interesting in its own way. And so I'd like to talk about first, it has an outsized role in humanity. If we look back and we say the word silver, we think of lots of different things, but in fact, it launched and destroyed many more civilizations than the pursuit of gold. It did many different things. It's the first currency. So if you go back and you look at Mesopotamia and the first cuneiform tablets, the very first mention of any idea of a currency is the word shekel. And so we still use the word shekel now. Sometimes when you have grandkids, you want to give them a few shekels, meaning you don't want to give them much. But a shekel was the first measured unit of currency, and it was silver. And so there are large numbers of things that are written. The law of Habernini contains what it takes to get a divorce, and it's described in how many shekels you must pay your wife to divorce her for various factors. So, and we look through, today, if we go to the 16th century, when they were mining a lot of silver in Bohemia, they began to stamp the ingots that they would produce, and they called them thalers, which became our word dollars. And so it remains, like I said, something that's quite important in terms of that. But it turns out it's got a lot of interesting properties that make it so that when you talk about silver minerals, many of them are very unique in the mineral kingdom, and that's what I'd like to talk about. I personally have been collecting silver minerals for about 50 years. So it's the 50th anniversary. I saw the other thing, and I thought about by the way, it's the 60th anniversary of quark, because I heard somebody complaining about quarks. And Murray Gell-Mann discovered or defined quarks exactly 60 years ago, yesterday. But the interesting thing about the reason that silver was so interesting to me is from when I was a child, and we lived in northern New Mexico, and my father just loved going out and pursuing treasure. He liked to go to old mines, and we went to the Silverton and San Juan area all the time. And somewhere around age 9 or 10, we were on the Telluride side of the Silverton area, and we went up to a very famous mill mining area called Tomboy. And like many young men and young women at age 10, if you give them a sledgehammer, they're going to break every rock. They're not really interested in the minerals that much, but I can remember distinctly I broke a rock that was opened, and there was a cavity, and in that cavity was a beautiful nest of silver wires. And it was just spectacular. And I ran over to my father. My father was a uranium chemist of some note. And I said, "Dad, why are they curled? What's going on here?" And my father, who he didn't speak a lot, he was not a particularly glib person, he says, "I think that's a great problem for you to think about." And that launched me down this path to try to understand silver from being a very young age. Unfortunately, that particular specimen got packed away when I went to college, and we've never been able to recover it. In my mind, it's about this big now, but I'm sure it was quite small, but it was important for launching this. And so I collected silver minerals, and I always came back to trying to think of why there are silver wires, why are they curly? But it wasn't until later in life, in my 20s, when I began to really build a scientific picture of trying to understand this marvelous element. And so really what I want to talk about is the properties of silver, and it comes down to being both a Goldilocks ion in terms of its size, and the fact that there's one little electron out there in terms of energy, which is just perfectly promiscuous. It really has a love affair with several different kinds of elements, in particular sulfur, but this love affair is fickle. And it's that fickle nature that allows us to have many different silver minerals, which change with time, give us a large variety of colors, despite the fact that silver only has, this metallic look, but we can go to this wonderful vermilion of a perovskite, or even the color, the blue in boleite, is associated with this strange little electron. That's a Bohr model of silver. It has, of course, the atom looks nothing like that. The Bohr model is a spectacular way for us to keep track of things, but the fact of the matter, electrons don't circulate around a nucleus. They do lots of weird things around a nucleus, way out there, just to balance the charge. But the energy levels are the things that are actually shown there. And there's one little electron sitting out there that has just the right energy level and just the right radius of silver such that it really wants to talk to other elements sometimes, but not make any long-term relationship. And therefore I call it the promiscuous electron. So I want to talk a little bit about silver first, and then we'll go through kind of the silver minerals. Now, silver is spectacular because of this electron. It's the most electrical and thermally conductor of all the metals. And so we like to think of, if you're going to build something and you want to have a great conductor, you think of gold. Silver is far more conductive than gold. Okay, gold's a pretty good conductor, and we use it often, but because it's less corroded, or has less potential for corrosion than silver. But silver is the most electrical and thermally conductive. The thermal conductive part's really going to be very important. It means it's very, very sensitive in terms of transferring heat from one part of a silver object to another part of the silver object. Silver's the second most ductile metal after gold. So we talked about what we could do with a single ounce or a wedding ring of gold yesterday. If you take 1 ounce of silver, it can be drawn into an 8,000-foot wire. Not nearly as much as gold, but that's still pretty darn ductile. So that's going to be an important property too. And then it's the most reflective element in the visible spectrum. So what do we mean by that? When you make anything that's metal, the definition of metal is that you have a metal bond. And what a metal bond means is the atoms share electrons easily. And so the sharing of the electrons defines the color. And so it shares electrons more effectively than anything else. That's the conductivity. But what that does is give a mirror-like surface or reflection to our visible range at least. So when you see an astronaut, for a long time they kind of had a gold-looking face mask so they wouldn't have too much reflection as they walked in bright sunlight on the moon or whatever. You notice that they're all silver now, and that's because it's a better reflector in terms of that. And the final thing that's really interesting about this is that this dangling electron, promiscuous electron, strange electron, means that it's a natural antibacterial material. So this was discovered pretty early, at least 4,000 years ago, that if you put a little silver in something, maybe you could stop, they didn't know what a bacteria was, but make something that was less poison. Some of the most famous stories, of course, is that Alexander the Great had a silver helmet, and he would only drink from the silver helmet because he was always worried that somebody was going to poison him. In fact, he did die of poisoning, took off the helmet, obviously. But this antibacterial thing is true. And so in the Western US, one of the big things is, it was not a myth, but it was a practice, and nobody quite understood it, is take a silver dollar and put it in your milk, and your milk will last a couple days longer than it would be otherwise. And it's very good with this single electron coming there to attract certain bacteria from growing. And we presently still use silver in lots of dressings for wounds. And if you're unfortunately going to get a catheter, it's definitely going to have a silver coating associated with it when it's inserted. So it's a pretty amazing material. But let's go to the mineral part of that. So if we start over here in the one corner, you can see a silver wire. That's a nice little silver wire from Guanajuato. If you add different elements to it, you get different kind of really cool things. So silver has a great relationship with sulfur, and the most common silver sulfide is shown there on the top. There is the acanthite. But the relationship with the acanthite and how that works is perhaps the most marvelous story in all the mineral kingdom. We're not going to spend a huge amount of time on it today because my acanthite talk is like 9 hours. Okay, but then you can also have what we call the ruby silvers. And so that's on the far side over there is a Proustite from Tornecillo in Chile. And the color is just spectacular. But the color changes with time on exposure to sunlight. So what does that all mean? Below that is a picture of Ellensburgite. That's an amalgam between silver and mercury. And it was the only way to fill cavities between about 1850 and about 1970. And so if you're of my age and you still have some old cavities filled with fillings, they're likely to be Ellensburgite. And it's perfect because you can mix it, put it in, it has an exothermic reaction, it expands and fills the cavity, and then it's just hard enough once it's done that to be able to be a useful part of your tooth. And then the last one is a silver chloride, so chlorargyrite. And of course, silver chlorargyrite is the basis of the original photography. So how do we make photographs? And we'll see that, again, this bond between this promiscuous electron and chlorine or iodine or some of the halogens is incredibly sensitive to certain spectra in the sunlight. When it strikes this, it breaks the bond between those. The chlorine or whatever it is will puff away as a cloud and you're left with native silver. And depending on how strong the light is how effective you break those bonds. And the silver that's left behind is the picture. And that's the basis of the first photographs in the 1840s. Silver was recognized as being very, very special pretty early on. So one of the greatest scientists that is underappreciated was Michael Faraday. And this is a picture of Michael Faraday. And in 1833, he discovered, remember, they don't even know what an atom is in 1833, right? They don't know anything about it. From a microscope, they're pretty lucky if they see something that's on the scale of a few microns. But he came up and discovered that he had been doing experiments with electricity and looking at salt water. Why did it conduct electricity, but pure or fresh water did not? And he discovered that certain solid materials, and the first solid material he found to do this was silver sulfide, argentite, could also conduct electricity, but they behaved really weird. He found that if you heated them up, they conducted electricity better. All other materials, when you heat them up, it conducts electricity less well. So he discovered the idea of a solid ionic conductor. His quote is here. He speaks that era's English, so it's a little hard to read. But he's basically saying that the sulfur to sulfur, compared to all other metals, is a spectacular conductor. And I don't know what it does, I don't know why, but it's really good. And I bet you we find some other good stuff. And that's kind of what he did. So when I said that he was underappreciated, Faraday came from a lower class upbringing. He had no schooling at all. But he was, first job that he was able to find was with a bookbinder. And when he went with this bookbinder, he was able to begin to read books. And he sort of barged his way in the back aisles to the Royal Academy and the Royal Society and listened to lectures and was able to bamboozle a job with Humphreys, who was the greatest chemist of the era. And he set him up in his own lab, and he is probably the basis for almost everything we understand about electricity, but was all later captured by James Maxwell when we have the Maxwell equations on how electricity works. But Maxwell basically credited Faraday with giving everything he needed to be able to do that. And so it's all based on the silver mineral. So when you're thinking about electricity and you're thinking about that revolutionizing our own society, it all came back to one guy working on a silver mineral. The earliest mention of really weird behaviors of silver minerals, though, was from the 16th century. This is Ecker's book, which was basically about processing materials. It's one of the more famous but rare books associated with early in mineralogy, or more in mining. And he has a quote that's great in this book. He says, take a piece of this acanthite, they didn't call it acanthite at this time, cut it lightly or scratch it, put it over a charcoal flame, heat it up, same thing that Faraday was doing, but what you could see is silver wires growing out of it. And he found that highly amusing. And he suggested everybody do that. And so we think of silver, we often think of wires. There's a couple silver wires. One of them on the far side over there is a Ellensburg wire. That's what defines silver for Ellensburg, perhaps the most famous silver locality in the world. It's large wires. It grows always out of a silver sulfide. The other one is from Sardinia. And then the middle is a picture from a study from 1883, which shows basically this wire is growing out. Couldn't really understand exactly why this was, and we'll come back to where it comes. But our definitive thing about thinking about silver is a little heat, maybe a little oxygen, maybe a little pressure, and we can change the character of it almost completely. So let's go back a little bit about silver before we go to the next stage. If you look up at the periodic table there, of course, everybody knows about the coinage metals. And so that's copper, silver, and gold. And they all share some properties. Okay, so the periodic table is organized that. And they all share one electron, which is a different energy state than the others, so it's kind of dangling. But gold is much too massive for that electron to be very active. And copper is has too little mass, and so it becomes easily to change valence states. And so silver sitting in there is the Goldilocks. It's just perfect, okay? And it's all those particular things. If we talk about gold, copper, or silver, we can say a lot of things about the crystallography that are always the same. You know, it's going to be cubic, it's going to be so on. But the real key is not those structures that we see in every textbook when we open and mineralogy. It's that interaction of that electron. And so it doesn't matter what the structure looks like. That's a representation we draw that turns out to be very misleading often. So again, all these are metals, so they all share electrons. They're all good conductors. But that sharing of electrons is what I want to focus on a little bit when we talk about the mineralogy. So a little bit of review of silver. I'll try to go through this a little bit fast because I'm certain it will not be on the test at the end. But silver is, it's relatively abundant in the crust. But when we look at different types of deposits, we can see we can enrich silver. So it's fairly common at any time you melt rock, you're going to be able to have some silver somewhere in that solution. And if we look across the middle red line there, again, it's going to be a logarithmic scale. As we look at that, we can look at silver deposits. One of the most important things which I'm going to touch on is going to be that silver-bearing galena. Okay, so it turns out that silver also has a rather fickle relationship with lead, which we'll talk about, all the way down to where we have native silver in terms of its abundance. If we looked at all the silver that was mined in history, it's about 80 billion troy ounces. So how much is 80 billion troy ounces? So if we take the density of silver and we turn it into a single cube, it's a cube about 55 meters by 55 meters, or a cube, okay? So you could easily fit it in the Rose Bowl. All right, it wouldn't quite top over the top of what the Rose Bowl is. It sits down from one side to the other, and then of course a football field is more like 100 meters long. So it fits well within that. So it's not that much material when you think about it. But if we look at silver, it's been mined since 1950, so I did it so roughly 75 years. 2/3 of all the silver that's ever been mined has been in that period of time. So that cube is still around, but it's because we've really only started mining this. We talk about silver all the time, but today's silver production dwarfs anything that's been in the past. And it's finding this silver concentration in all different kinds of deposits, in particular copper and so on. So the worldwide occurrence of silver, it's on almost all base metals. When we have from high temperatures to low temperatures, one of the really interesting things with that electron is the supergene process, where we have weathering, enrichment, moving the silver ions around. we get some of these very exotic minerals. And the mineralogy we get there really reflects the geochemical environment that it's in. So let's look kind of at a silver deposits you might expect with high temperatures. What you have then is the magmatic fluid. It's carrying some of this. As we bring this up, we get a base metal, but always we're going to basically take some of that material away through fluids and veins, circulation from the surface, and it's those areas that are going to give us the really interesting silver minerals. And we don't see the same thing or nearly as profound for example, gold, and we see it even more amazing for copper because it goes back to this size of what the silver is. So if I would take anything away from that, silver solubility, if we change the acidity, if we give it acid, if we give it temperature, it becomes more soluble and we can move it around. But as soon as we introduce it to sulfide, or we put chlorine in solution, just like we had in gold, in this case, it's going to change the way it's going to interact. So this is kind of, again, just the framework to set up where we're going with the minerals, because you won't believe some of the things I'm going to tell you later on unless you're like, believe this. This is kind of a review again associated with your coinage metals. When we look at this, we look at the ionic radius. And so you can see gold, of course, is the largest one, but gold is a much more massive, many more protons and neutrons than the other two. And then copper is the smallest. But if you look at this, this radius just turns out to be just right. And if you describe again, the nucleus here is only a head of a pin, but those last electrons are a football field away. And so trying to find the right relationship between holding that all together and letting those electrons be tightly bound to you is truly a Goldilocks kind of thing. And silver is Goldilocks. And it will turn out that if it has a relationship often with lead, and then these semi-metals of arsenic, antimony, and bismuth, and then it really likes this set of antiions in the end, sulfur in particular, but selenium, tellurium, and chlorine. If I take all the mineralogy associated with silver, it's going to be pretty much on that graph except for the word mercury. Mercury is a special material, which we'll talk about a little bit in the end. So if I just look at the classical mineralogy associated that, I would find, we could stack these elements together, but it doesn't really tell you about its interaction. So I'm going to give you the silver mineral scope when we're going to go through metals and alloys. We're going to talk about sulfides, we're going to talk about sulfosalts, and we're going to talk about halides. First of all, just to leave this in a weathering environment, anytime you have oxygen or water around, silver does lots of things. It moves quite easily. And because of that, we're going to revisit this sometimes and look at different things that are going in this. So this is the geochemistry playbook. Again, it's really not important because I'll come back to this in terms of understanding this, just realizing that adding water close to the surface and oxygen makes silver really interesting. So let's start out with the native elements. Typical native elements that we see in terms of silver, something like, of all the silver that's mined, 2% is native silver. So it's a pretty small percentage. When we see silver, it's almost always in wires. But there are two other times we don't see it in wires. One of them is a spinel twin. This is a nice spinel twin. It's about 5 inches across. This is from a relatively recent deposit in Peru. And what you see is crystals of silver which are growing as octahedrons, but they're twinning such that you get this herringbone pattern. So this would be a natural solution or a natural crystal that you would expect for silver. If I look at all the rest, typical silver, there's another herringbone on the top. That's from Charnicillo. That's about 10 inches across. So it's a pretty spectacular silver plate, but it's the same herringbone pattern. The common most way over there is like a wire. That's from Dukat in Russia. That has, in each one of the grooves of that silver, is plated on gold. So it has a relationship with gold too, but it's kind of a strange one. That one just happens to be really remarkable in that it's not a mixture of gold and silver. The gold comes in later on and it's on the outside, and there's a wire. We'll come back to the wires. Sometimes you find it in cubic crystals. That's a Ellensburg piece down in the lower corner, or you find it in more complicated crystals, which are almost always dodecahedrons, and that is the last one that's on this side, and the lower side is from the Keweenaw Peninsula. When we talk about native silver, we're going to either see crystallization, and it's almost always rapid growth crystallization that gives you spinel twins. So you have a botopellis piece on the bottom of the lower for you, the right. You have a very nice one from Chanacillo there that's about 5 inches across also, from showing again this, and then these spectacular wires. That's a wire from Freiberg. Freiberg has been a special interest for me for many reasons, but that Freiberg wire stands about 6.5 inches tall. And if I take just that silver and I convert it to the acanthite that it must grow to, I get a block of acanthite that's about 1 foot by 1 foot by 1 foot. So what you're looking at is a large-scale decomposition of another mineral to be able to make that. So keep those kind of in the background. And now let's go to silver sulfides. And again, silver sulfides, I like to say they have a strange marriage between the sulfur and the silver there, and it runs hot and cold. Because I'm going to tell you that every single silver sulfide that we find in nature experiences phase changes as we change the temperature. What the heck do we mean by phase changes? We mean that its structure changes. So if I have a silver coordinated with a sulfur, we think about where those parts are and how far they are apart. If we change the temperature, that bond's going to stretch, and it's going to change the location of where that silver and sulfur are coordinated. So the classic way to look at that is acanthite. When we go buy an acanthite and we find a nice one that's a Guanajuato piece there on the left-hand side, it looks cubic. In fact, that is the high temperature form of silver sulfide. But as we lowered the temperature, it froze in that structure from the visual perspective, but internally it has a monoclinic structure. All those sulfur bonds to the silver bonds snap back into a different direction, but left the outside looking like this. So it's kind of like a pseudomorph, but not really. And then on the other side, you can actually see a low temperature form. So it formed at a temperature, in this case, less than 170 degrees C, which is just the monoclinic form. So that's a piece from Arispe. So those are the same chemistry, but they were formed at different temperatures, giving a cubic appearance versus sort of appearance that looks more like a Roman sword. If I was in a classical chemistry class and I asked you to tell me what silver sulfide looks like, you would first draw the sulfur framework. So we got some elements here, so it's silver 2, sulfur. We're going to put these together. And then we're going to ask, where do the silver elements go? In the textbook, it's going to show you one silver talking to a couple sulfurs. But because the electron is fickly touching one sulfur for a while, then another, we actually could never tell you where the silver is relative to the framework of the sulfur structure. So the sulfur structure is defining what's going on, and the silver is in this cage of the sulfur. But if we heat it up, the cage expands. If that cage expands, sometimes the silver can escape. It can move somewhere else in that particular mineral. And that's giving us this change in both structure and why we grow wires. So if I look at that last plague here, there's just the possible silver sites for any acanthite that you see given the structure, this cage of sulfur. It is not the way we're taught to think about chemistry, or most of the time in mineralogy. We get a single model that's like balls with sticks, and it just doesn't work for the silver around sulfur. So this is kind of an attempt to show, basically, in this case, on a high temperature, or I'm sorry, a low temperature acanthite, so the monoclinic structure. We show a monoclinic structure here. So silver is the blue, the interaction with the sulfur is the yellow. Then we're going to go through a phase change, and that phase change, this is in, unfortunately, is in Kelvin, and nobody uses Kelvin, but Anyway, and so what we see is that we suddenly go to this phase change, which makes it cubic. But where the silver is when we're in that cubic thing could be anywhere. We can actually go to very high temperatures, and then what we go is to a completely different body-centered cubic at high temperatures. But we don't have many of those specimens that are around at that high temperature. So we go from this monoclinic, kind of Roman sword looking thing to this cubic looking thing as we change temperature. Is all we did is expand that cage around that silver and allowed it to do its thing. So this is kind of just my eye candy for different acanthites. The top one on the left-hand side there is an acanthite that's on a Proustite crystal, actually, from Freiburg. But what you're seeing there is a sixling twin. So I took 3 of these cubes and I put them together, and you can see the top that looks like a drill bit, and that's those cubes coming together. The second one on the top is another Freiburg piece. It's about 6 inches tall, and you can see it filling the cavity, and you see it's cubic, so I can tell you what temperature it had to form at. The bottom here is the Guanajuato cubes. This is, to me, my favorite acanthite that I own because it's just so spectacularly looking like galena. It's about 2.5 inches across. It's not huge. And then finally, the word acanthite comes from roots for the thorns. And so as we go to low temperatures, typically acanthite shows you these growths that look like thorns on a bush. And so that's an example of that, and that particular one happens to be from Jochenstall. So if I put all those things together, again, this is not a diagram that will mean much to anybody, but it's the way I think about things. I can actually look at all these elements interacting. And down here, I'm just going to ask myself, if I'm going to talk about 2 axes, I want to care about how much silver I have in there, or maybe some other elements like lead and copper. And then I want to ask how is it interacting with either the sulfur or things that look like sulfur. So they could be, selenium, tellurium, chlorine. And I'll put those on this axis. And so all these things down here, acanthite, and we'll talk about aguilarite, nominite, hessite, they're all down in this corner. There's silver with 1 or maybe 2 of these other elements. But as I move up here, I can add copper or gold. And as I move up this axis, I begin to enter into a realm of even new complexity that we're going to talk about that never is taught in chemistry. And it's about disordered structures. So that's where we're going. We're going to try to make it so complicated nobody knows what we're doing at the end. Okay? So here I'm going to do some substitution with different of those anions or add something to it. The top picture here is the nominite. So I've taken the same thing that I have for acanthite, but I removed all the sulfur and I put it in selenium. Okay, and so that's one of the largest selenium or nominite crystals in the world. Often nominite's just a massive material. That's from Idaho. And if I replace the selenium and I put in tellurium, then I get hessite. If I take half of the selenium and half of the sulfur, then I'm going to get aguilarite. So I can make all these different minerals by just replacing those anions. If I take the original acanthite, but I remove some of the silver and I replace it with copper, then I get holpaite. And so that's holpaite's about 2.5 inches tall. And you can see some green on the outside. What's happening is it's absorbing some of the copper, interacting with the atmosphere, and you're growing malachite. And so these is, kind of the things that you want to get around here as you change the mineral chemistry just a little bit. But every one of these things looks like what we did with the original acanthite. If I change the temperature, I'm going to go through a phase change for every one of these minerals. I'm going to go from something to something else, usually from a monoclinic to a cubic. So keep that in the back of your mind. Let's go talk about sulfosalts. The sulfosalts are, we often call the blood of the bull because the 2 most common are Proustite, which is on the left-hand side, which is a silver arsenic sulfide, or perargyrite, the one shown on the right side, in which we have antimony instead of the arsenic. These are the most coveted silver minerals for silver collectors. And the real reason is because their colors are always so spectacular, right? So they always say, I'm a silver collector. They say, well, why do you like black uglies? Well, guess what? I have a red one. Okay, it's not that common, but anyway, I have a red one. So these, though, take us to our next lesson about how strange that electron behaves. So, by the way, just for those that are keeping score, the perovskite there is about a 6-inch cluster of crystals from Charniceo. It was originally traded out of Harvard. It was in a large block of calcite. And Cal Graber basically dissolved all the calcite, which is a really hard thing to do with perovskite, and was able to produce a few dozen of these pieces. And it's one of those things which you're surprised. The perargyrite and the others, a 2.5-inch crystal, or crystal cluster, this from St. Andreasburg in Germany, which is kind of the capital of perargyrite crystals that look really great. So as I go through these, I'm now doing the sulfur salts, but I want to add just a little bit something else. It won't be quite important yet when we do just the ruby silvers, but it's going to be really important as we go from the ruby silvers to everything else. We're going to add lead. Same diagram as kind of we had before. Over here, no lead, but it's just the silver sulfides. But as we add lead, all the things we have in terms of perargyrite, perovskite, we can all take a little lead in that structure, and it gives a spectacular range of minerals which are really important historically. So let's go back now, keeping in mind we're down in the lower left-hand corner of that diagram, or at least on the edge as we go up here, as we add a little sulfur to this to get to where we're going to go. The stars, of course, of when we say the ruby silvers are perargyrite perovskite. The bottom one is a perargyrite from, on the left-hand side, from Fresnillo, and then the Charniceo perovskite. And the color in this is the thing that's the interesting part of that. So what does that mean? So let's look at the colors. The colors are always a little different for perargyrite and perovskite, and I'm going to tell you why in a minute, but thinking one of them has arsenic and one of them has antimony, and that's what's going to be controlling the color, but it's going to be controlling the color for a reason that you won't expect. It's not a chromophore. It's going to be a bond length that's going to be in the atom itself. But we'll get the molecule itself. So here's a really nice set of perovskite, and if you look at this, this is from Schneeberg. It's about 2.5 inches tall. Good color, and if I go to a textbook and it's going to show me what this looks like, that's going to be the picture. You're going to see it. You're going to see, something that's going to be basically hexagonal, and the interaction is the yellow is the sulfur. Then if I see a couple red things within that, that's going to be, in this case, the arsenic, and the white is the silver. And so if I look at that structure, it's like, yeah, I could pack all that stuff in there and I get a crystal. But that's not actually what's going on. So what's going on is really we're having this fickle electron decide to talk to the sulfur for a while or talk to a different group of sulfurs. And so if I'm looking at this, the yellow here is a sulfur, and in this case, I'm looking down the c-axis, and this is the silver interaction. This is called an Einstein physics or Einstein electrodiagram to describe the interactions. The sulfur's got some size here, meaning that they have some responsibility for moving around too. But the silver is really large. If I turn it on its side and look straight down it, I typically think about the silver interacting with two sulfurs, because the sulfurs will form a pyramid with, at the apex of that pyramid is going to be either the arsenic. But in fact, I can interact with 6. 4 around and 1 above and 1 below. And so at any given time, I'm going to be interacting in that particular direction. So there's a bond that's between those, but that bond changes with time. And that bond is very highly sensitive to temperature. So the mobility in sulfides and sulfur salts, including the ruby silvers, is a thermal effect. And it leads to the conclusion that the physical heating is required. But in fact, thermal motion isn't just heating, it's also excited by radiation. And radiation, when I mean this, is a photon, light. So it does exactly the same thing as heating it at. So ruby silvers, in particular peroxide and prustite, are very sensitive to ultraviolet light because of the length of the bonds that it's connecting between the silver and the sulfurs. And so if I look in a UV light, I'm going to break a bond. Now that bond that we break is related to the sulfur, but it's the bond that holds that little triangle together, and so we call it the silver arsenic bond. So if I take a nice piece of prustite and I take it to the bright sun, which has the appropriate UV signature to it, and expose that, I will eventually break the bonds. And if I do that, what I'll see is a white powder will begin to grow on the prustite. The prustite will begin to darken and it will grow silver on the outside. And so if I do this long enough, I get a black prustite crystal with a white powder, which is the arsenic recombining with oxygen from the atmosphere. And I can't stop this process once it starts. So as soon as I shine a light on this, I'm starting a reaction. If I grow some silver out of that, I have a charge imbalance, and the prustite's going to eventually decay, no matter what. So you have a choice. You can always take the prustite you have and hope that it's never been exposed to UV light, and you could put it in something that has no oxygen environment, store it in a nitrogen container, and it will last a long time. But if you keep it in your case, eventually it's going to turn color, and there's nothing you can do about it. You can't reverse it. You can't shove the silver back in it. But the color is so great, it's the reason we collect it. This is an example of one that is beginning to gone too much light. This is from Schneeberg also. It's about 2.5 inches across. You see the black dots on there. Those black dots are actually silver. So that's silver coming to the surface. I've washed off the white powders associated with the arsenic there. And to me, that's a fabulous specimen because it's reminding me that this particular mineral is so reactive in a way because of this relationship between the Cili electron and the sulfur atoms. Perargyrite usually has a much darker color. And that's because the antimony bond back to the sulfur is stronger and shorter. So the color from prustite and perargyrite is what we call a semiconductor band color. And so light comes in, it excites the bonds, and you get a color depending on where these bonds have a particular energy length. And so for the arsenic, it gives you that very, very red color, meaning that's the only color it didn't absorb. For the antimony, it's usually darker. Now occasionally, as that one crystal is on the far right-hand side, you can get spectacular color when you come light through it. The good part about this is these bonds are much more difficult to break than those in prustite. So they'll eventually probably, if you decide you want it under UV all the time, darken. But the top picture there is a complexly twinned cluster of prustite from Huancavelica in Peru, and that's a natural color that you're going to see eventually for all these, a silver reflectance. But most of the time you can get some red through that. The one with nice pyrite on the epitaxial growths on it is from Fresnillo, and the other one is from St. Andreasburg. Just a couple more to leave because historically perargyrite has been the most important silver mineral for many mines because of being able to process it. These are two pieces from Tasco, Mexico. The one on the left for you is actually huge. That's about the size of a hand. It weighs about 2 pounds, so it's got a lot of good silver in it. The other one's much smaller, but it's shows a spectacular shine associated with perargyrite with time that it develops. But just like acanthite and silver sulfide, a phase change is going to occur for these two. So we actually have other ruby silvers, which are low temperature forms of some of these minerals. In the middle there is zincanthanite. It's the Moroccan piece, and you can see these little hexagonal plates. That is the low temperature form of prustite. So you heat that up to around 190 degrees, maybe C, then it will be, it's going to turn to a structure that's going to give you the Proustite. On the far side and the other is pyrrhostilpnite, and pyrrhostilpnite is the low temperature form of perargyrite. And then another ruby silver that's not appreciated very much for what it is, but it also has a phase change in it, is myargyrite. And the name myargyrite just means bad silver because it has less silver than acanthite, but it has the same, because it has one less sulfur, it has a red glint to it, so it belongs in the ruby silvers. So I just relieved this with the Proustite. Great set of experiments was done in 1837, which heated up Proustite crystals to grow silver wires out of them, just like you saw out of the acanthite. I think it was probably a crime to do that, to ruin a Proustite crystal that way. But nevertheless, I want to leave you with all ruby silvers are light sensitive, same as a thermal. So we already got this one electron doing thermal things and radiation things. So let's go to the next. So outside these, but still silver sulfides, are silver sulfide is stephanite. It's called brittle silver. These three, the one that's there on the far left-hand side is actually almost a 3-inch crystal from Pribram. Below is probably recognized from the iridescence, is a husky mine stephanite. And the middle one, or the last one over there on the right-hand side, is a series of stephanites from Freiberg. And the reason it's called brittle silver is that if you ever get a chance to have a really good stephanite and you decide you want to glue it to like a little stick or something like that, you're screwed. Because it's likely that no matter what you do, unless you really soften that glue, you're going to break this material. It's very, very brittle. And so the name is appropriate, but it's, from a standpoint of a silver, it is a really interesting mineral, but it's not a ruby silver. So these are all going to be black or black and shiny. And so another Freiberg piece in the top in the red. Below that is a Fresnillo silver. It's not hexagonal, but it is almost always found as pseudo-hexagonal. And the last piece is one of the prized stephanites in my collection because it's named after Duke Stephan. And this one happens to be one from his original collection. And it's about 5 inches tall. It's a pretty amazing piece. The other one that goes with this class, it's not quite the same, is polybasite. And so here's a couple polybasites. One on the left-hand side is from Arispe, Sonora, and the other is from Fresnillo. And this gives us a chance to begin to look at what we call disorder in minerals. So things are going to get really complicated. If I go look at the chemical formula, and I'm taking a chemistry class, we think that when we see 6 coppers together and 2 sulfurs, that's telling us something about the bulk chemistry. It is the bulk chemistry, but it's not telling you how they interact. As soon as we get to things like polybasite, and actually just barely in stephanite, we're actually going to begin to enter in which we get clusters of silver interacting with some sulfurs, and clusters of silver interacting with another body, sometimes lead, but mostly lead, but not in this case. Sometimes it's antimony. And they have 2 different structures. And we're going to stack those structures on top of each other. Okay? And the reason we can do that like Legos is because they have basically holes. So if I say I have a silver here, I don't know where it is in the structure until I know how it's interacting with the other elements. And so this disorder gives you structures that begin to look like these. So in this case, this is the structure associated with polybasite. And what we see here is we see got a little copper, we got a little silver, and we're going to stack these, and they're going to have these different colors. It's not really important to know exactly what this is, but you see something strange going on. You see a layer here that looks like we have a structure, then a layer here, which we have a different structure, and then another layer that looks like this original bottom one here. So when we begin to do this, we have to move away from thinking about things just interacting in one set of cells, but we have to think of interacting with blocks that we stack together. So that means that we have to tell you which silver atom goes where. And so we call those disordered structures. This has been a curse to mineral collectors. Because if we were going to go collect polybasite and we replace the antimony with the arsenic, we would call it pyrrhite. And we would be happy. But mineralogists have screwed us because they now want to have a series, in this case of 6 things, telling us where each of the silvers are. So you now, if you go to a textbook and you look up polybasite, it will say polybasite dash TAC, TAC. And then you'll look over there and there'll be a series that says, telling you where each of the disorders are. But as a mineral collector, you don't care. You just want to know, be able to collect the minerals in peace. So if I look down here, I've got 3 different structures. I got a polybasite structure, TAC. I got a pyrrhite, what I would call pyrrhite, but unfortunately we don't call that pyrrhite anymore. So we have a different polybasite for the structure telling us that in different subtext on the bottom. And then the final one is another one like a polybasite, but it's a final structure that is just slightly different where the disorder is. But if I looked at all those, I want to say that's polybasite and pyrrhite. But I want to let you know that that's wrong, but unfortunately the splitters in the world have made it so it's really difficult to become a mineral collector. One of my best friends that works on these is a chemist at Harvard, Frank Hoytsch, and he is a splitter royale. We really get screwed when we begin to look at more and more complex silver sulfosalts. This is what I would always call Freibergite. So you are familiar probably with the name Freibergite. It's a silver in-member, kind of what we think of as tetrahedrite. Okay? So here's 2 pieces of different Freibergite. This is the large Bolivian piece. This piece is from Freiberg itself. And we just think of it as a mineral that has a lot of silver. There's the structure that you see down here. Look at the structure though. The structure separates out everything. We've got a silver, 6 of these, but we got a silver, some more 6, but with a different valence because it's unbalanced. And we have to stack that with copper and something else. And that something else can be iron, it can be cadmium, it can be zinc. Okay, and then we have to balance the antimony along with some sulfur, leaving one hole that's left. You could do that 12 different ways. So there's no longer any Freibergite. And there's actually no longer any tetrahedrite. They're all names that are unpronounceable. But the kind of interesting thing is, they wouldn't work that way if silver was not so fickle with the electron. So we got screwed as collectors because we get so excited about all the things that silver can do with that electron. But again, I will always collect those as Freibergite. These are all related to every sulfosalt. You get that, so you often see them growing on each other. This one over here on the left is a polybasite crystal with stephanite clusters on top of it. You just change the temperature slightly, and you rob all the silver out of the polybasite and make stephanite. And that's what happens when you have disordered structures. In the lower corner over there, that's a polybasite replacing ferrargyrite. And again, the replacement is because you change the temperature. Let's talk a little bit about adding lead. Lead is an amazing thing. The large crystal you see there is diaphragmite. Lead and silver have a relationship that is hard to explain. It's just easily to take molten silver and put it in a galena structure. In fact, all the silver that was mined up to around 1200 or 1300 was actually in galena. And then it was removed through a process called copulation, in which you basically heated the material, oxidized the lead, removed the lead, and you're left with silver. So the huge silver mines that made Greece so famous at Laurentian and so on, they're all galena. So this relationship, which is shown in the phase diagram over here, is something that we struggle with all the time, but it makes lots of really interesting minerals. So silver and where the silver and the lead fit in a structure is quite complicated. This is also a diaphragmite, that's a ferrolizite, there's a andorite, and you can kind of look at this thing. These gives you infinite number of crystals, or infinite number of formulas. If you go to the present IMA index, there's about 236 different silver minerals. And about 80 of those have to do with some amount of lead. Now, I try to collect every silver mineral you can find, but I am only allowed to collect 198 because I don't buy into the splitting. Okay, so it's a lot easier when you're obstinate. But of course, I'm also incredibly fortunate because the mineral that's named after me is exactly one of these lead splitters. Okay, so I'll leave you a little bit with the lead story. There is, it makes a lot of things because of the disorder. I want to then go quickly to the alloys. Alloys are mixtures, so they have structure, but they're mixtures. And so unlike all the minerals that we talked up to this point except for the native, they actually have a metallic bond. So when we add silver to antimony, or silver sometimes to arsenic, but mainly antimony, we make a metallic bond. So we make discrosite. Or if we add it to mercury, we make a series of amalgams, which Ellensburg is the most common. And you can see the fillings that were there. And these are a special set of elements because they only form with this metallic bond in very, very special conditions. The most famous of these are, of course, discrosite. So there's a very large discrosite. That thing over on the left-hand side weighs 6 pounds. And that's a Moroccan one that just came out, relatively recent. I'm quite certain if I die too early, that will be mistaken for a doorstop. And above you can see a very nice discrosite crystal, massive crystal from St. Andreasberg on top of crystallized arsenic. And the last is the famous locality for discrosite blades, and that's Prevert. Let's get to halides before I get off here. Halides are really, really interesting. They form bonds. And when we make these bonds, it's that electron moving around, and it's easily disturbed by radiation, a photon again. And it really is true. If you take a chlorargyrite, you take an idoargyrite, you expose it to light, you're producing chlorine gas and leaving behind silver. So these are a couple of pictures of which I try to reserve in terms of this. My favorite, I love chlorargyrite because it's a late stage mineral. It always forms, and usually it takes silver and you have chlorine coming in later on. And this is one of these from Calico. It's actually an egg. It's a little bit larger than the AAA size egg. It's hollow. This was originally all silver, and then through time it had enough exposure to the chlorine. It's a different density, and so it grows an egg. It's hollow. That's a very nice chlorargyrite crystal up from Bolivia. And these are idoargyrite, which was the film emulsion originally associated with being able to put together a photograph. So what I wanted to do today was just give you this immediate flyby of this spectacular mineral without, showing you too many nice pictures. The story is much more complicated than I gave it today. It is my goal in life before I die to finish my book on silver, but right now I'm at about 25,000 pages, and most people tell me that's too long. So I'm working, and my goal is ultimately to see you someday in the future with the tome on silver, which will tell the whole story from its beginning in Earth to the end, where we see a spectacular spinel twin from the Keweenaw Peninsula. So thank you very much.
Okay, thank you very much. Wow. Okay, so I want to be the first. So can you come back next year for our 2025 acanthite themed, and we'll just put you on, and that's the whole symposium. All right. Questions? Okay, yes, right here in the middle.
On the iridescence on like the husky?
Yeah, so I worked quite a bit on the iridescence, and for a long time it was a little bit hard. We see iridescence on lots of sulfides, and almost always it's an exsolution of something, right? Well, we were having a hard time with this, and so I got together with George Rossman, who was actually on my PhD committee, roughly in the Eocene, and we decided to do a very special modified ramen. And it turns out that iridescence is an incredibly fine coating of a silicate that contains a little potassium. And when we made that material and we sprayed it onto things, not necessarily onto another stephanite, we were able to reflect the light in that rainbow pattern. So it's not like a copper exsolution or something like that. It's a late stage, very, very fine coating of a silicate.
Okay. Caleb.
So with the fructites from Chinnercio, a couple of those have phthalate on them. How is that coming into play with that?
So phthalate is a really interesting mineral. There's a group of minerals that are held together with a totally different type of bond. If you get me going on this, Caleb, you're really in trouble. Because that bond is a van der Waals bond. And so phthalate is a very, very thin mica-like material, and it's held on to the layer below it through this van der Waals force, which is not a bond, but it's an attraction. And so you get a book of phthalate. Phthalate is a mercury silver sulfide. It's probably got a little bit of amalgam in it. And so it really comes from almost everything in Chinnercio has quite a bit of mercury in it. But when this material is clean, this particular sample that I talked about, it had a huge amount of phthalate. And so it's a fortuitous accident. I own about half of the phthalate. I'm going to be a phthalate fork.
The other question I have
Terry.
is the cuprite crystals from Russia forming mirror-site on them. How is that?
Okay, so the mirror-site that's coming in there, of course, mirror-site's a copper iodine. It's iodine. I don't think it's chlorine. I think it's iodine. And what you're really looking on that is basically a late-term warm solution, which you're adding a halogen. And so you can get some pretty nice mirror-site. You know, the mirror-site, really good mirror-site crystals are Broken Hill, and they're red. I mean, they're as red as you get. And the stuff you get from the Russian stuff is much grayer or yellow almost.
Okay, I hate to do this, but we're going to have to cut it off here. So let's thank our speaker one more time.